Welcome to the analog electronics course. This is lecture number 35 and today the plan is that I am going to start talking about a new module. This module is about power amplifiers. So, we are going to start with basic power amplification. Now, when we started this course, at that time also we discussed this very briefly. We had discussed why we are doing analog circuits at all, right. When you have a transformer, for example, a transformer is a linear passive device, right. You can amplify the voltage with a transformer, right. Let us say on the primary you have a voltage V1 and then the turns ratio is 1:100, then on the secondary you will have a voltage 100 times V1. You can amplify the voltage like this, but while doing this step up of the voltage, your current is going to step down, right. Net power is going to be conserved. V1 times I1 is going to be equal to V2 times I2, whatever happens, right, because there is going to be conservation of power and this is a linear passive device, nothing extra is going to happen. So, the entire point of learning this course, right, the one and only reason why we learnt this entire setup with MOSFETs and so on and so forth, amplifiers, right. There is only one reason why we learnt it, so that we can make V2 I2 more than V1 I1, okay, so that we can somehow manage amplification in terms of power. Right now, when you say amplification in terms of power, I do not ever mean that you are going to violate the law of conservation of energy, right. You have to satisfy. So, somehow from outside you are going to input some DC power to satisfy the entire setup. Okay. So, we are going to have a 2-port network, right. Imagine your transformer, right. You have got V1 I1 and you generate V2 and I2. Okay. So, we want V2 times I2 to be much more than V1 I1, right, and how is that going to happen? That is going to happen only if I apply extra power from outside. Let us say all these are grounded. Okay. So, I apply extra power from outside and this power is going to be a DC. This is going to be a signal, right. So, the idea is that you are going to take my voice from the microphone, right. You are going to take my voice from the microphone and then, so this is the microphone, this point is the microphone, right, and then you are going to amplify the power in my voice. How are you going to do that? With the aid of an external power supply. So, you use an external power supply, okay. You take its help, amplify my voice from the microphone and play it on the loudspeaker. Okay. So, that is the entire plan, right. This is the holy grail of analog circuits. This is why we are learning analog circuits. Okay. If you can't amplify the power in the signal, then there is no need to do analog circuits at all. You should do transformers. Fine? Okay. Great. Now, with this understanding, we are going to proceed further. We are going to look at our very basic common source amplifier. So, the plan is of course, that I am going to apply the input signal at the gate of the common source amplifier, all right. So, this is, if it is common source, you are planning to apply input at the gate of the amplifier. Now, you need a load. The load is my external load. Right. I do not want to impose the DC bias conditions on the load. The load should only take signal power, and for that normally what we do is we put a huge coupling capacitor, fine, or a decoupling capacitor over there. Okay. Now, this capacitor is so big, right, that it's a short circuit for all AC signals. For all signals it is a short circuit, whereas if you are thinking of DC, then the capacitor is naturally an open circuit. Fine. Now, we have to bias the MOSFET, and to bias the MOSFET you can bias it with a current source, for example, right. You can use a current source over here on the at the drain, you can use a current source and bias it, but to keep matters very straightforward, very simple, let us for now use an inductor to bias this MOSFET. Now, this inductor, let us choose this inductor value to be so large, the inductor is so big that for all DC signals it is a short circuit. For DC the inductor is always a short circuit, okay. But we are going to choose the value to be so large that for all AC signals it is an open circuit, all right. So, inductor impedance is J times omega times L, omega times L. We are going to choose L so large that whatever the value of omega is, J omega L is very large, and this is as good as an open circuit. Fine. So, this is the plan. So, the inductor is DC short, AC open, the capacitor is an AC short, DC open. Okay. These are huge valued capacitors and inductors. Now, automatically the bias point at the drain is VDD, the DC operating point of this MOSFET. VDS is equal to VDD. Okay. VGS, let us come to VGS. So, let us apply VGS such that I get maximum swing. Okay. So, let us apply some VGS, let us not worry about it. So, if you remember our convention, small letters subscript capital letters is something which is the combination of both the small incremental signal plus the DC operating point. Small subscript small was just the incremental signal, capital subscript capital was the DC operating point. Okay. So, this was our convention. The only one that is not over here is capital subscript small, and capital subscript small is nothing but the Laplace transform of small subscript small. Okay. Just reminding you, refresher. All right. Now, for this capital VGS, and so for this DC operating point, capital VGS is the gate to source voltage and capital VDD is the drain to source voltage. So, for this DC operating point, suppose I get a certain current capital I subscript capital D, and remember the inductor is a short circuit for DC, but an open circuit for AC, which means that the incremental current cannot come through the inductor. Okay. As far as the incremental current is concerned, it is an open circuit. The current through the MOSFET is small I subscript capital D, which is equal to capital ID plus small id. And naturally what is going to happen is that the incremental current is going to come solely through the capacitor small I subscript small d. And remember, the capacitor is a short circuit for incremental signals. So, the incremental current will happily come through it, but it is an open circuit for DC, which means that capital ID, no portion of capital ID can come through the capacitor. Okay. So, we have cleanly separated the signal from the DC operating point over here. It is very clean. All right. Now, if you think of the voltage over here is right. There is a DC operating point part which happens to be equal to VDD plus a small signal, an incremental part. Let us not call it small signal. I am sorry, I am not going to call it small signal. Small or large is irrelevant, incremental part, right. So, there is a DC part, there is an incremental part, and the sum of the two is the actual voltage at that node. Now, what is going to happen? As far as the DC is concerned, the inductor is a short circuit, which is perfect, but as far as AC is concerned, that is incremental is concerned, the capacitor is a short circuit and the capacitor is an open circuit for DC, which means the voltage over here is going to be small v d, right. The current through the load is small I d. All right. So, this is our setup. It is a very straightforward circuit, right, nothing much is over here. There is only a MOSFET and there is an inductor capacitor and then there is the load, and that you are exciting with the help of a signal and a bias voltage, and here is a power supply. Okay. You can't have components lesser than this, right. Which are the components that dissipate power over here? Does the inductor dissipate power? No. Does the capacitor dissipate power? No. Okay. These are all passive lossless components. Inductor and capacitor do not dissipate any power. Okay. So, VDD is generating power. The MOSFET can consume power. The load is going to consume power, but of course, right. As far as the signal is concerned, these are not producing any power at all, because the current into the gate is always equal to 0, assuming forget about all the capacitors and so on and so forth, right. Let us forget about the capacitors, parasitics, let us forget about those. Then these two are not really generating any power, this is 0 power. Okay. So, VDD is producing power, MOSFET is consuming, load is consuming, fine. So, this is the setup over here. If you want, you can add a resistor in series with the signal source. It is not going to make any difference because the current is 0. Now, let us see what is going to happen in this circuit. So, suppose small VGS is a sine wave, all right, and suppose just suppose that this sine wave is going to produce a response in small I t, which is also a sine wave. Ordinarily it is not, because the MOSFET is a square law device, right. But if you assume that the higher harmonics are not there, let us say I filter out the higher harmonics through some mechanism, okay, then I can assume that small I d is also a sine wave. The current in the load is a sine wave. Okay. So, this is the assumption we are going to make right away. Now, when small V G S goes up, what happens to small I d? If I increase small V G S, what is going to happen to small I d? It is going to increase, right. G m times small V G S approximately is small I d, if it is a small signal. If I decrease small V G S, then small I d is going to decrease, right, below 0. If I make small V G S go below 0, then small I d is going to go below 0, right. Then the net I d is going to go below the bias current, right. What is the smallest small I d? What is the smallest drain current that you can have, you can tolerate? When you talk about swing limits, remember we did swing limits a long time back, right. When you talk about the swing limits, the smallest drain current is always equal to 0. Okay. You can't have a current smaller than 0, it can't go negative, all right. That tells me that the maximum amplitude of small I d is equal to capital I d. Okay. So, if you plot, suppose this is capital I d and I am plotting small I sub capital D, then when I increase V G S, this increases, but when I decrease V G S, this decreases, and the maximum amplitude that I can have is equal to capital I d. So, basically you are going to start from capital I d, you are going to go all the way up to 2 I d, come back to I d, come down to 0, right. That is the kind of waveform that you can have. This is the largest possible amplitude you can have, right. So, I can choose the amplitude of small V G S such that I get this largest possible waveform, all right. So, let us do that. Let us say that small V G S is such that I get this largest possible waveform over here, fine. Then just like this, we are going to start looking at the voltage V d. So, let us look at the voltage V d. So, small v sub capital D. Now, small v sub capital D has a DC operating point value of how much? Okay. So, the DC operating point value is VDD. Now, when I increase VGS, if VGS goes up, ID goes up, right. When ID goes up, what happens to small Vd? Small Vd actually becomes negative, right, which means that small v sub capital Vd is going to decrease. So, when the input voltage goes up, the drain voltage is going to go down naturally, right. How much can it go down? What is the best case scenario? The best case scenario is the overdrive voltage, right. VDS has to be more than VGS minus VT to make sure that the MOSFET remains in saturation. All right. So, let us say we abide by that rule, that MOSFET is going to be in saturation. Okay. In that case, this is the kind of waveform we are expecting. Best case, the largest possible waveform for small v sub capital D, where this much is nothing but VGS minus VT. Remember, these are things that you did when you worked with the swing limits of the MOSFET. Now, let us just simplify. VGS minus VT could be 0.2 volts, right. Let us simplify, all right. Let us say that it is 0, just super simple. So, I am simplifying, I am saying that let us say this is not even VGS minus VT, this is equal to 0, all right. So, in that case, the maximum amplitude of small v sub cap small v small d is equal to, so this is small v small d, right, VDD, and the extra stuff. What is the extra stuff? The extra stuff has an amplitude of VDD. So, it starts from VDD, comes down to 0, goes back to VDD, then goes all the way to 2 VDD, comes back to VDD. Okay. If I make this assumption that it is not even VGS minus VT, not even 0.2 volts, it is 0 volts is the minimum. Fine. So far so good? Okay, great. Now let us look back again. Let us look at the following things. We are going to first look at what is the available power from the input source. What is it? Available power from the input source is source squared divided by 4 Rs. So, this is the maximum power that you can draw from the input source. This is small VGS. If you say that it is the amplitude, then it is not even 4 Rs, it becomes 8 Rs. It is a sine wave, okay, and we are not talking about that root 2 adjustment and so on. Small VGS is just the amplitude. Okay. This is fine. This is the available input power. Now, let us see how much power is supplied by the DC power supply. So, there is a DC power supply over here of value VDD, and how much current is it pushing? It is pushing ID amount of current, which means that the power supplied by this DC power supply is VDD times ID. and these are at DC, right. VDD and ID are both DC quantities. So, there is no half or anything. Okay, great. Then let us find out what is the power delivered to the load. So, the load sees a voltage small Vd across it and a current small Id through it, okay, and naturally the power in it, but small Vd and small Id are both sine waves. So, the power in the load is half of small Vd times small Id. Okay. Now, what is the maximum power that you can possibly deliver to the load? Okay, what is the maximum possible power in the load? We have found that the maximum possible amplitude of small Vd is nothing but Vdd, and we have also found that the maximum amplitude of small Id is nothing but capital Id, not 2 Id. Okay, 2 Id is where it is reaching the amplitude, the signal part, the amplitude is capital Id, and this is maximum possible. Vdd is not even correct, it is actually smaller than Vdd, right. The actual amplitude, if you take into account Vgs minus Vt, then it is smaller than Vdd, it is not even Vdd. Fine. Now, you can define efficiency as the amount of power that you have drawn from the power supply, right. You take that into account and you take into account how much power did you deliver to the load. Okay. So, power delivered to the load divided by power drawn from the power supply is defined as the efficiency. So, efficiency how much is that? Maximum efficiency is VDD ID by 2 divided by VDD ID, which is equal to half, or in other words 50%. So, if I draw energy from the supply, only half of that is going to be delivered to the load. Where is the remaining half gone? The remaining half obviously has gone into the MOSFET. The MOSFET must have burnt it as heat, because there is no other power consuming device over here. This is just the load and the MOSFET. Let us check what is the power consumed by the MOSFET. How will you do it? How will you work out the power consumed by the MOSFET? The power consumed by the MOSFET is the voltage small v sub capital D times the current small I sub capital D. Right, this is the instantaneous power, but we have to work out the power consumed over one full cycle, right, energy consumed over one full cycle, because it is changing with time. And then look, for the sine wave you do not have to do this integration at all, because you know the answer. Okay, but how did this by 2 answer come? The by 2 came because somebody, right, or maybe it could have been you, did this calculation a long time back and you recall it. Okay. But in this case we have not yet done this calculation, or maybe we have, let us just break it up. Okay. So, this is going to be integral over one period and then the average. Fine. And if you look at it carefully, small I sub capital D is nothing but the DC part, which is capital ID, plus the AC part, the DC part which is capital ID, plus the AC part which is capital ID sin omega t, sin omega t. Okay. Now, you can always generalize and say omega is 1 hertz or 1 radians per second, in which case this omega will go away and this t will become 2 pi. Right. Suppose omega, I mean there is not going to be any difference whether omega is 1 radian per second or 2,500 radians per second, it makes no difference, the answer is going to be the same. Therefore, you can always say that let us do the calculation with 1 radians per second, in which case these become set numbers, you do not have to manipulate too much. Okay. So, this is I d of t, and then V d of t, what is that? V d of t likewise is capital V d d minus capital V d d sin omega t. Okay. So, this is what we have, and this is just an exercise, we already know the answer. The answer is going to be what? The answer is already there here, 50% power is delivered to the load. So, 50% power has to go to the MOSFET. We already know the answer, this is just an exercise. So, let us do this exercise. Now, what you want to do? You want to take I d times V d d, and then you want to take V d d I d sin t, then there is minus V d d I d sin t, which cancels this term out, and then finally, you have got minus V d d I d sin square t. Okay. And a lot of people do not like calling it t at all, they just call it theta. Instead of t, you can call it theta, and suddenly a lot of people will feel more comfortable. Okay. Somehow sin theta is more comfortable than sin t. Right. So, I d times V d d, integral of that, these are both constants, integral from 0 to 2 pi is just going to be 2 pi. Okay. And then when you divide it by 2 pi, it just comes out. And then the remaining part and then sine squared theta can always be broken up into cos 2 theta. Yes, how do you do that? 1 minus cos 2 theta by 2. Is sine squared theta. Okay. And then once again what is going to happen is I have got VDD ID by 2 integral d theta, that is going to give me from 0 to 2 pi, that is going to give me a 2 pi, and 2 pi and 2 pi are going to cancel out, and what is going to come out from the 1, instead of the 1 I will have VDD ID by 2 coming out. Okay, I still have one more integral to do, integral cos 2 theta d theta, right. You can replace d theta with d 2 theta for example, or you can replace 2 theta with some alpha, right, substitute 2 theta as alpha, this becomes pi in that case, and you get a half outside. So, now you are integrating cos alpha from 0 to pi, right. So, integral of cos alpha is sin alpha. When you plug in sin alpha to be 0, you get 0. When you plug in sin alpha to be pi, alpha to be pi, you again get 0. So, the net result of this integral is going to be one big 0. Okay. So, therefore, you have VDD ID minus VDD ID by 2, and that leads you to the answer that you expected, VDD ID by 2. So, there, that is how you actually do it. Okay. So, what did we figure out? We figured out all of the following. We had the simplest of all circuits, common source amplifier, right. Biasing was done with the help of an inductor, capacitor was used to decouple the DC operating point from the load. Fine. Input was applied on one side. What did we see? We saw the following. We first saw that the available input power was so much, but the power delivered to the load was so much. Okay. If RS is large, suppose RS is large, then I immediately can deliver a much larger power to the load than the original input source could have. Okay. This can be made to be significantly larger. Okay. VDD ID by 2 can be significantly larger than half VGS squared by 4 RS. If RS is, I mean, all you have to do is have a weaker microphone. Okay. RS is larger, all right, smaller VGS. Now, weak microphone, you can always get power amplification, right. That weak microphone would not have been able to drive the loudspeaker. With the help of this circuit, now you probably can. This is number 1 observation. Next, power supplied by the DC source is VDD times ID, nothing else. ID is the current, VDD is the voltage, VDD times ID is the power supplied by the DC source. The power delivered to the load is small vd small id by 2. I have not made any assumptions in this, right. When I say that maybe the largest amplitude of small v d is v d d, then I make an assumption that the MOSFET is in saturation and the smallest voltage that you can tolerate is 0. Okay. Otherwise, this is always correct, no matter what. There are no assumptions. There is no assumption in this also, right. These two are assumption free. Given the circuit, this is always going to happen. This is always going to happen. Then from here to here, small I d, the maximum amplitude is capital I d, and small v d, the maximum amplitude is capital V d d. I have made certain assumptions in this, right. And then after making those assumptions, those are all pretty general assumptions, nothing very significant in those assumptions. All that we are assuming is that we have got a sine wave over here, number 1, and then the this is overly optimistic. For example, capital V d d is too optimistic, the amplitude is not really going to be so large. So, what does that mean? That means that the maximum efficiency has an upper bound of 50% and it is not even 50%, we know it is smaller, right. For example, this one is overly optimistic, V d d is overly optimistic. So, 50% is overly optimistic, you are never going to reach 50%. Okay. So, think about it, you are trying to play something on your cell phone speaker phone, right. You are trying to play some music on your speaker phone, on the cell phone, right. You are trying to make the entire audience listen to that song. As much power as is going out of that speaker phone, that much power is going to be burnt as heat inside the power amplifier. Okay. So, your battery, let us say, is producing 1 watt, right, half watt at best, half watt is going out to your audience, half watt is going to burn just as heat. All right. I mean, clearly you try to sell this power amplifier to the best company, Samsung or whatever, Motorola, and they are going to laugh at you because this is no good, right. And this power amplifier is there everywhere, right. It is not just at the speaker, this is also there at the antenna. Suppose you are trying to talk to a base station which is far away from your cell phone, right. I am trying to give the example of the cell phone again and again because the cell phone today is the most popular electronic object in your pocket, right. So, your cell phone is trying to communicate with a base station that is far away, you need an antenna, and to drive the antenna you are going to use a power amplifier because you are going to push a lot of power through this antenna. As much power as you push, at least that much power you are going to burn as heat. All right. So, this is just not good, this does not cut it, but unfortunately this is how things are. All right. Now, we had a constraint over here, and the biggest constraint that is causing this 50% is this. We were telling ourselves that we want to keep the MOSFET in saturation. All right, there is nothing else over here. VDD times ID is a golden truth, you cannot violate. Small v d small I d by 2, you are not going to violate. Okay. So, the only thing that gives me these numbers is I apply this constraint, I get these results. So, this must be something that we have to relook at. All right. Let us take another example. Let us take a second power amplifier circuit, okay. And instead of the common source amplifier, maybe you can use the common drain amplifier, okay. That also has large input impedance. You probably won't bother about the common gate amplifier that much, because the input impedance in the common gate amplifier is small, not large. Even if you do bother about it, then you are going to make sure that the input is a current source, not a voltage source. So, the strategy is going to change. Let us not worry about the common gate, let us do a common drain amplifier. Okay. And let us not worry about body effect. So, we will assume that V t is constant and everything. And once again, what we are going to do is, ordinarily you are going to put a current source over here, or you are going to put the load over here, over there at the source. Instead, we are going to put the load AC coupled to the source, and we are going to achieve this bias point ordinarily through a current source. In this case, let us achieve the bias point with the help of a huge inductor, right, and we make this inductor of such large value that it is a short circuit for DC, but an open circuit for incremental signals. The capacitor is a huge capacitor such that it is a short circuit for incremental signals, but open circuit for DC. Fine. So, this is our setup, and then again we do the same design as before, right. This is going to take a current capital ID. The current over here is small I sub capital D, which is the superposition of capital ID and small I small d, and the current going through the capacitor is only small I small d, fine. And then now it is not the drain voltage anymore, now it is the source voltage. The drain voltage is fixed at VDD. The source voltage is 0 because of the inductor, right. The DC operating point of the source voltage is 0, and then there is a small signal, an incremental signal part of it, which makes it equal to small V s. Okay, the capacitor is a short circuit for this particular incremental voltage. Let us not call the input voltage VGS, let us call it the bias voltage, let us call it VG, and let us call the input voltage as V in, just so that we do not make a mistake. And you can have any series resistance over here. Okay. So, this is our setup, and let us see how it amplifies power, if at all, or what is going on in this circuit. Now, how are we going to do that? We are just going to first look at what is the power supplied by the only source of power over here. It is VDD times small I sub capital D. All right. So, it is no longer like our earlier case In the earlier case we had VDD times ID, right. In this case the power is being supplied, it is VDD times small I sub capital D. So, power supplied is VDD times small I capital D. All right. What is power delivered to the load? If you assume sine waves, then the power delivered to the load is small I d times small v s divided by 2. And then what is the power consumed by the inductor? Is power consumed by the inductor? Never. Okay, inductor is not going to consume any power. Is power consumed by the capacitor? No. So, these two are zeros. Okay. The other one that is going to consume power is the MOSFET, okay, and we will have to work out the efficiency. How are we going to make the efficiency? Work out the efficiency. The efficiency is going to be the power in the load divided by the power supplied by the DC power source. Fine. So, this is how it goes. Now, let us make our plots. Let us try to find out what is the maximum amplitude of small I d that you can possibly have. Small I sub capital D is the sum of capital I d and small I d. So, the maximum amplitude of small I d has got to be capital I d, because small I sub capital D can never be smaller than 0. Okay. Amplitude means it is going both positive as well as negative, right. So, the maximum amplitude of small I d is capital I d. So, I am not even bothering to draw, you understand from our, just like our previous discussion, right. The graph pretty much looks the same. Okay. Fine. So far so good. Let us look at this source voltage, or in other words let us try to find out what is the maximum amplitude of small v sub small s. Okay. What is the maximum amplitude at the source? What is it? This can rise all the way at best up to VDD, right. The source can't go beyond VDD, right. It is going up and down, this voltage is going up and down incrementally, right. When it goes down, it is going down below ground. When it goes up, it has to maintain this MOSFET to be in saturation, which means that at best it is going to be VGS minus VT less than VDD. If I say that VGS minus VT is nothing, then at best it is going to go all the way till VDD, which means that the maximum amplitude of small v sub small s is nothing but VDD, and that too that is overly optimistic. So, too optimistic. Okay. Which means that the maximum power, possibly maximum power you can deliver to the load is nothing but VDD ID by 2. That is the maximum possible power that you can deliver to the load. What is the power that is being drawn from the source? The power that is being drawn from the source is VDD times small I sub capital D, which is equal to VDD times capital ID plus small id. Okay. And then when you have to find out the power, this small id is changing with time. So, you have to integrate over one period, right, but when you integrate small id over one period, you get 0, right. Small id is nothing but capital ID cos or sin omega t, right, and then integral of sine from 0 to 2 pi is going to be a big 0. So, this is not really going to give you any contribution. You can do the integral, all you will get is 0. Okay. So, the power drawn from the DC source is VDD times ID, average power. The maximum power that you can deliver to the load is VDD times ID by 2. Therefore, what is the efficiency? The maximum possible efficiency is once again just about 50%. In fact, it is lesser than that, because we have got one of the two, the voltage amplitude, this is too optimistic, right. We know it is not even VDD, it is actually smaller than VDD. All right. So, look, whatever we are doing, our efficiency seems to be 50%, right, half of the power seems to be being burnt in the MOSFET itself. So, this kind of strategy is not quite working out. Okay. However, this is the general principle of power amplifiers. Power amplifiers work on this principle only, nothing else, right. Power amplifiers are simple amplifiers that are going to be used to blast power into the loudspeaker or into the RF antenna or wherever power is required. Okay. So, let us stop here, and then in the next class we are going to look at more efficient ways of doing the same thing, right. Typically the constraint that we have, even here the constraint is the same. Why did we get VDD ID by 2? The reason we got it was because we wanted to make sure that the MOSFET remains in saturation. So, we now have to start violating that condition, right. So far we have held that condition to be golden, right. Till lecture 35 we have said that, let us make sure that the MOSFET is always in saturation. In lecture 36 we are going to stop saying that, we are purposely going to make it not remain in saturation, and then we are going to see what happens. Okay? Thank you.